Now we've already differentiated exponential functions, but up till now we've never integrated them. Now the most basic one to integrate would be e to the x. We know that if we differentiate it, we just get itself. So if we integrate it, obviously it comes back to just being itself. And the only thing we need to remember, if it's an indefinite integral without any bounds on it, then we need to add a constant. Now it also stands to reason that when we differentiate e to the power of some function, we know how to do that. We differentiate that function, in other words, we get f dash x, and we bring that down the front, and then we just rewrite everything that we were given. So we already know this rule. So it stands to reason that we can reverse this rule and go exactly back the other way. Now, a perfect question would ask us to integrate the exact thing that we get when we differentiate it. So in an ideal world, we'd get a question where we've got f dash x out the front, and f dash x being the differentiation of this function that's up here. And then when we're asked to integrate that, it's quite straightforward to just say we must get e to the power of that function, and then we just need to add our constant. Now, you will not always get these perfect questions like this, but it's still worth knowing this rule, because when we do these questions that aren't perfect, what we're trying to create is this situation, because this one is easy and it works in with something that we know really well. Now, even though we won't always get perfect questions, we can adjust the questions that we're given to turn them into perfect questions, and that's how we move ahead. Now, we can only do it if we have a term, I say out the front, because what I'm talking about here is this term here that's out the front of the actual exponential expression. Now, if this term that's out the front has the correct power of x, and what I mean by that is that x squared, x cubed, x to the power of 4, if it's the correct power of x, but the numbers or the constants aren't right, we can adjust for it. But if it's the wrong power of x, we actually just don't have the skills so far in this course to integrate it. Now, if there's no term out the front there, and we're just asked to integrate e to the power of some function, well, there always is a term, isn't there? I mean, ideally, this is 1. There's not nothing there. There's 1 there. So we always have notionally a 1. But if it looks like there's nothing there at all, that's okay, as long as the highest power of x that was actually in our function was 1. Now, to explain this, I've written in red here a third rule. So we've got the most basic rule. Normally, textbooks will put this second rule in, and then they'll come to this third rule. I actually prefer to just stick to these two. And I'd be more than happy if these two are the only two you write down. I don't think it's strictly necessary to write this one down, but if you like it, go for it. Now, the reason I think it's not strictly necessary is here we're saying what happens when we differentiate e to the power of. Now, this is a little function of x, isn't it? It's just written ax plus b to show that it's not x squared or x cubed or anything like that. It's just a really simple function where the highest power of x is 1. We've got some x's and some numbers. Well, you can differentiate this using the exact same rule as this one. Ax plus b is just a function of x. So what do? Differentiate ax plus b, you'll get a, bring it down the front. And that's exactly what happens. So you can see that this little rule here is kind of unnecessary to memorize if you know this one. And this one helps you with any function of x, not just ax plus b. So it's really more all-encompassing. Now, what's happening in this one, though, helps us understand here what I'm talking about when there's no term in the front. Because in a perfect world, it would be most ideal if we are asked to integrate the thing that we got when we differentiate it, because we know that going from here to here is differentiating, and going from here back to here is integrating. So if we're asked to integrate this is a perfect question. It's quite easy. We can just say, well, it's e to the power of that function, and we just need to add a constant. This is a perfect question. But what if we don't get the perfect question? What if we're just asked to integrate this, e to the power of ax plus b? There's no a out the front here. What do? Well, we can adjust for it. And my method is we write the question that we want to do. So here I've changed the question I've been given to one I would prefer that's got the a out the front. And a is just a number, a constant. Now to adjust for that, out the front of the whole integral, I can put 1 over a, because 1 over a times a gives me 1 anyway. So effectively this question is equal to this one, but this one's easier for me to do because it's got the A out the front, and that follows this rule. I know how to get back from here to here. So now this part's easy to integrate. I just get e to the power of ax plus b. I have to add my constant. But remember, I've still got my 1 over a out the front, which you can write as a 1 over a out the front here, or you can put that whole term over a. It's the same thing. Now, this is a rule that lots of people like to remember, and they'd remember it like this. Let's say, let's get a different colour. This, this part equals, and they could cut to the chase and say it equals this part. So I join those two up. If you're writing down this rule, I just put this part and this part together in a box.